This video is on different types of equilibrium constants. There are many different types of equilibrium constants that describe specific types of reactions. And so after watching this video, you should be able to write down the chemical reactions that correspond to the different types of equilibrium constants. You should also be able to identify the equilibrium constant for the given reaction. And some equilibrium constants have subscripts that indicate a specific type of reaction. Now in the previous video in equilibrium, we talked about K in terms of activities and K sub C in terms of concentration. K without the subscript is in terms of activities. It's the proper thermodynamics equilibrium constant. Often equilibrium constants are written in terms of concentrations, and I denote that as a K sub C. Now there's also Kw, Ka, Kb, Ksp, and Kf. Kw is the ionization for water. Ka is the acid dissociation constant. Kb is the base dissociation constant. Ksp is the solubility product, going from solids to aqueous ions. And Kf is a formation constant. And so ionization of water, it's actually a very, very important equilibrium constant. You're going from liquid water to hydrogen ions plus hydroxide ions. And so water is a reactant, and hydrogen ions and hydroxide ions are the products. If we write down the equilibrium expression, we do products over reactants, coefficients become exponents, pure solids, pure liquids don't appear because they have activities of 1. And so we end up with Kw equals hydrogen ion concentration times hydroxide ion concentration. Now if we rewrite this reaction, write it backwards, so we have hydrogen ions plus hydroxide going to water, that equilibrium constant would be 1 over Kw. Remember, if you switch products or reactants, then you take the inverse of the equilibrium constant. Now this is actually a very important equilibrium because for all aqueous systems have to follow this equilibrium. And so for all aqueous systems at equilibrium, you can always determine hydroxide ion concentration from hydrogen ion concentration or hydrogen ion concentration from hydroxide ion concentration. So for example, if an aqueous solution has a hydrogen ion concentration of 10 to the minus 6, we can determine the hydroxide by solving for the hydroxide ion concentration. It's equal to Kw over hydrogen ion concentration. Kw at 25 degrees Celsius is 10 to the minus 14th. And so 10 to the minus 14 divided by 10 to the minus 6 gives us a hydroxide ion concentration of 10 to the minus 8th. Now, this equilibrium is also gives us a pH of 7 for neutral solutions at 25 degrees Celsius. And so we can calculate the pH of a neutral solution at 25 degrees Celsius. For a neutral solution, the hydrogen ion concentration is going to be equal to hydroxide ion concentration. And so we can substitute hydrogen ion concentration for the hydroxide ion concentration. And so we end up with Kw equals hydrogen ion concentration squared. And so the hydrogen ion concentration is going to be equal to the square root of Kw. And again, at 25 degrees Celsius, Kw is 10 to the minus 14th. And so hydrogen concentration is 10 to the minus 7th. The pH is minus log of the hydrogen concentration. That's how we get the pH of 7. And so the pH of 7 for 25 degrees Celsius for a neutral solution comes from the Kw. Now it's kind of interesting, Kw is actually temperature dependent. Most equilibrium constants are temperature dependent. And so the pH of neutral solutions or pH of pure water actually depends on temperature. And so at 50 degrees Celsius, the pH of pure water should be 6.64. And again, it just follows the temperature events of Kw. And so we also have acid dissociation constant. So we have the little subscript A. And so you're going from acid to hydrogen ions plus anion. You could also have hydronium ions. Remember, hydrogen ions and hydronium ions are the same thing. And so for Ka, you always look for hydrogen ions or hydronium ions. We can actually write down the Ka reaction one of two ways, either the acid breaking apart into hydrogen ions plus the anion, or water plus the acid going to hydronium ion plus the anion. Now again, if we switch it, so we write the products as reactants, reactants as products, we have to take the inverse, and so that second reaction has an equilibrium constant of 1 over Ka. Ka is actually how we determine the strength of an acid, and so typically when we're talking about a strong acid, we mean it completely disassociates. We're not talking about how well it dissolves something. And so based on how much disassociates, we call HCl a strong acid. If you add HCl to water, most of the HCl molecules actually break apart. It has a very large Ka. Now HF is really, really nasty. It's very dangerous. If you Google HF, you'll find people have died from HF. It's actually used to etch glass. It's much nastier than HCl. I'm scared much more of HF than HCl. But in terms of dissociation, we'd call HF a weak acid because it only partially dissociates. Only a small fraction of HF molecules actually break apart when it's added to water. Now, some acids have multiple protons. They're called polyprotic acids. And so the strength of acid does not depend on how many ionizable protons it has. And so in this movie we have phosphoric acid. It has 3 acidic protons, 3 protons they can lose, but they're not lost easily, so phosphoric acid is actually a weak acid. Now, whenever you have a acid with multiple acidic protons, the Ka1 is always greater than Ka2, is always greater than Ka3. So it's always easiest to remove the first proton, then the second proton, etc. And so here's a table of some acids. And so again, Ka1 is for removing the first, Ka2 is for removing the second, Ka3 is for removing the third proton, and for an acid, the Ka1 is always greater than the Ka2, which is always greater than the Ka3. And so for phosphoric acid, that first reaction there corresponds to the Ka1. And so you're forming hydrogen ions plus dihydrogen phosphate. Now, if you take the dihydrogen phosphate and you remove one of its hydrogen ions, you form hydrogen phosphate, and that's the Ka2. And then that third reaction, we take the hydrogen phosphate and remove the last hydrogen ion and form phosphate ions, and that's the Ka3. And again, typically these protons are not removed all at once, but they're actually removed in steps. And so it's kind of an interesting question we can ask, what is the Eckhart constant for the following reaction? We have phosphoric acid going to 2 hydrogens plus hydrogen phosphate. And you should recognize that is the sum of the 2 reactions above it. So if we add the reaction corresponding to Ka1 and the reaction corresponding to Ka2, we get the reaction that we're looking for. When you add reactions, you multiply the corresponding equilibrium constants. And so the equilibrium constant for our third reaction is Ka1 times Ka2, which is equal to 4.3 times 10 to the minus 10th. And so at acid dissociation, we have where an acid is going to hydrogen ions or hydronium ions. We also have base dissociation, symbolized by a Kb, where we have a base going to hydroxide ions. Now we can actually write Kb's in 2 ways, with or without the water. For a strong base, we can just go breaking apart. So we have sodium hydroxide going to sodium ions plus hydroxide ions. For a weak base, we actually always need that water. So ammonium plus water going to the ammonium ion plus hydroxide ion. Now weak bases typically don't have any hydroxide. They form the hydroxide by ripping off the hydrogen ion from water. And so again, ammonia is your typical weak base. It's got that lone pair, which is able to rip off the hydrogen ion from the water, forming the hydroxide ion. And so again, if we take the products reactions reactions products, we take the inverse of the Eckhart constant. And so that second reaction, where we have ammonium ion plus hydroxide ion going to ammonia plus water, that Eckhart constant is going to be 1 over Kb. And just like for Ka, we use it to talk about the strength of an acid. Kb, we use it to talk about the strength of the base. The larger the Kb, the stronger the acid. The larger percent of the molecules dissociate. And so Kb's of strong bases are considered to be infinite. They're very, very large. So sodium hydroxide, all alkaline metal hydroxide, heavy alkaline earth hydroxides are strong bases, have very large Kb's. Ammonia is our typical weak base. And so only a small fraction of those molecules form hydroxide ions. But again, we should be able to use these to recognize Eckhart constants for reactions. And so looking at this reaction, we want to know what is the Eckhart constant for the following reaction. Now in acid-base chemistry, often we're looking for hydrogen ions, hydronium ions, or hydroxide ions. And so notice we have hydronium ion as a reactant. And so that should lead us to think about 1 over Ka. And then if we look on the other side, we see we have the nitric acid. And so the Eckhart constant for that reaction is going to be 1 over Ka of nitric acid. And so all this is the reaction corresponding to Ka of nitric acid written backwards. And again, if you switch products reactants, you take the inverse. Here's another one. What is the Eckhart constant for this reaction? And so again, for acid-base chemistry, often we're looking for hydrogen ions, hydronium ions, or hydroxide ions. And so we see the hydroxide ion is written as a reactant. And so that should make us think about, okay, it's probably going to be a 1 over Kb. If we look on the other side of the hydroxide, we see ammonia. And so the Eckhart constant is going to be 1 over Kb of ammonia. And again, this reaction is just the reaction of Kb for ammonia written backwards. And so it's going to be the inverse. We can look at something a little bit more difficult. So what is the Eckhart constant for this reaction? Now notice we don't have any hydrogen ions, hydroxide, or hydronium ions, but we do have a strong acid and we do have a strong base. And so sometimes if we're asking what is the economic constant, what we want to do is write down the net ionic equation. And so we have to figure out which ones can we break apart. And so HNO3 is a strong acid. If you have 1 molar HNO3, it means you have 1 molar hydrogen ions, 1 molar nitrate ions. Strong acids completely dissociate in water, and so nitric acid is just hydrogen ions and nitrate ions. Now we see KOH, that's a strong base, and so strong bases are also completely broken apart. So if you have 1 molar potassium hydroxide, you actually have 1 molar potassium ions, 1 molar hydroxide ions. And then KNO3 looks like ionic solid, but you have that aqueous. And so if you have something that looks like an ionic solid, but it's aqueous, it means it's broken apart into aqueous ions. Now for the liquid, it's just a liquid. It doesn't break apart. And so we can take this reaction and we can substitute the ions indicated. And so again, this is the reaction. Now if we break apart, say the nitric acid is hydrogen ions, nitrate ions. The potassium hydroxide is potassium ions, hydroxide ions. Potassium nitrate, potassium ions, nitrate ions. The water does not break apart. They're molecules. If you have 1 mole of water, you have 1 mole of water. Now if we notice that the nitrates on both sides and potassium ions are also on both sides. And so those are referred to as spectator ions. Ions that do not react are spectator ions. And now if we write the reaction without the spectator ions, we get the net ionic equation. Now we should recognize that the economic constant for the net ionic equation is equal to 1 over Kw. Now the economic constant for the net ionic equation is also the economic constant for the reaction that we started with. So it's kind of cool. To determine economic constants, so often what we have to do is figure out what is the net ionic equation. Once we figure out the economic constant for the net ionic equation, we figured out the economic constant for the reaction that we started with. Kind of cool. We can look at another one. So here we have HF plus KOH going to KF plus water. Now HF is a weak acid. It only partially dissociates. If I have 1 molar HF in a bottle, I have 1 molar of nastiness, or basically 1 molar of HF molecules. Very little hydrogen ions and very little fluoride ions. Its Ka is very small. And so if I have HF aqueous, I cannot break it apart. It's a weak acid. Now KOH, again, is a strong base, so I can break it apart. Potassium ions, hydroxide ions. In a bottle of KOH, you have potassium and hydroxide ions. You do not have KOH molecules. KF looks like ionic solid aqueous, so that means if I have 1 molar bottle of potassium fluoride, I actually have 1 molar potassium ions and 1 molar fluoride ions. And then the liquid does not break apart. And so if we take the ions and substitute them where we can, so HF, weak acid, does not break apart. Potassium hydroxide does break apart. Potassium fluoride does break apart. And then my liquid water does not break apart. And so I notice that I have potassium ions on either side. And so potassium ion is my spectator ion. If I write the reaction without the spectator ion, then I get my net ionic equation. Now, if we look at this one, we notice that we have hydroxide as a reactant. So that tells us, okay, 1 over Kb. If we look on the other side of hydroxide, we see the fluoride ion. And so economic constant for this should be 1 over Kb of the fluoride ion. And so again, we start with that reaction on top. We found the net ionic equation. We found the economic constant for the net ionic equation. And so that economic constant is for the net ionic equation and for the reaction that we started with. We can look at something a little bit harder. And so what is the economic constant for this reaction? Now, I don't see any way of breaking up. Ammonia is a weak base, so it doesn't break up. HF, a weak acid, doesn't break up. Ammonium ion, weak acid, doesn't break up. And then I have the fluoride ions. And so we're not going to go the net ionic equation in this case. But what we can do is try to figure out a series of reactions that when we add them up, comes to the reaction that we're forming. And so if we notice that we have the ammonium ion, then maybe we should think about having the reaction corresponding 1 over Ka of the ammonium ion. And we see we have HF, and so maybe we should think about the reaction corresponding to the Ka of HF. And so now if we add these two reactions, after we add them, the things coming on both sides will cancel, the hydrogen ions, and we'll actually get the reaction on top. When you add reactions, you multiply the corresponding equilibrium constant. And so if we add these two reactions, we multiply the Ka of HF times 1 over Ka of ammonium ion. and that's going to be the Eklund constant for the top reaction. Now it's kind of cool. We did this in terms of Kas, but there's no reason we can't use the Kbs. And so notice that we got ammonia as a reactant. And so we could think about ammonia going to ammonium ion plus hydroxide, ammonia plus water going to ammonium ion plus hydroxide. And we could think about water plus F minus going to HF plus hydroxide, but written backwards. And so when we add these two reactions, again, we get that top reaction. If you add the reactions, again, you multiply corresponding Eklund constants. And so the Kb of ammonia times 1 over the Kb of F minus gives us the Eklund constant for the top reaction. And so it's really kind of cool. What we found is that the Eklund constant for that top reaction is equal to Ka of HF divided by Ka of ammonium ion. It's also equal to Kb of ammonia divided by Kb of F minus. Those two have to be equal to each other. Now this is actually a result of the conjugate relationships that you should learn from acid-base chemistry. Ka of the acid times Kb of its conjugate base is equal to Kw. But it's also kind of cool. What this tells us is that if HF is the stronger acid than ammonium ion, then its Ka is going to be bigger than that of ammonium ion. And so the Eklund constant for that top reaction will be greater than 1. If ammonia is a stronger base than the F minus, then the Eklund constant for the top reaction is also going to be greater than 1. Now it turns out that the stronger acid is always on the same side as the stronger base. And so for this reaction, the ammonia is stronger than F minus, HF is stronger than ammonium ion. So the stronger acid is always on the same side as the stronger base. And so if you need to figure out if the Eklund constant is going to be greater than 1 or less than 1, you actually just need to figure out which side either the stronger acid is or the stronger base is. It's better to figure out both, but because the stronger acid is always on the same side as the stronger base, we actually only need one of them. And so because the stronger acid and stronger base is on the left-hand side, stronger in this case means more reactive. At equilibrium, we should end up with more products, and so the Eklund constant for this top reaction should be greater than 1. We can also look at this reaction. And so the question is Eklund constant going to be greater or less than 1? And so actually just need to figure out which side has a stronger acid, which has or stronger base. And so we see that in the products we have HCl, a strong acid. And so the products is stronger. It's going to be more reactive. So we should have more reactants at equilibrium. And so our Eklund constant should be less than 1. If we look at this one, we have ammonium ion hydroxide going to ammonia plus water. And so again, we just need to figure out one of them. Hydroxide is going to be a stronger base than the ammonia. And so the reactants are stronger, they're more reactive. And so at equilibrium, we should have more products. And so K should be greater than 1. Really kind of cool. And so we talked about Kw, Ka, Kb. Ksp is the solubility product. And so for Ksp, you always have a solid, ionic solid going to aqueous ions. If we write down the equilibrium expression, products of reactions, coefficients become exponents. Pure solids, pure liquids do not appear because they have activities of 1. And so notice that we just have, in this case, Ksp equals barium ion concentration times the sulfide ion concentration. The barium sulfite solid does not appear because it has an activity of 1. If we write down the reaction, swapping products and reactants, again, the Eklund constant is going to be 1 over the Ksp. If you swap products and reactants, then you take the inverse of the Eklund constant. We can look at a few examples. And again, notice that pure solids, pure liquids do not appear. And so for these reactions, Ksp is just going to be equal to the aqueous ion concentrations to some power that correspond to the coefficients. Again, please remember the coefficients become exponents when you write down the equilibrium expressions. And you should also remember that in ionic solids, they actually are composed of charged ions, but the net charge is 0, so the charges have to cancel. So on the top one, we have 1 barium per 1 sulfate, ratio of 1 to 1 because barium is a +2 and sulfate is a -2. On the second one, we have 3 chloride ions for every iron ion, because iron is a 3+ in this case, and the chloride is a -1, so you need 3 of the chloride ions per every iron. In the third one, you have 3 magnesiums for every 2 phosphates. 3 times 2 is equal to 2 times 3. And so again, ionic solids composed of ions, but their net charge has to be 0. You should also recognize the polyatomic ions. It's very important to recognize them because they stay together as a group. And then on bottom, we have the magnesium phosphate. And so for KSPs, they describe solubility. The larger the KSP, they're more soluble. And so sodium chloride table salt is very soluble, has a very large KSP. Silver chloride has a very small KSP, so it's not very soluble. And so again, we're asked the reaction, what is that chemical constant? And so I don't see any acids or bases, but I see lead nitrate aqueous, looks like an ionic solid aqueous. And so for ionic solids but aqueous, I can write down them as aqueous ions. And so lead nitrate is actually equal to lead ions plus nitrate ions. Potassium iodide, aqueous is potassium ions, iodide ions. And then potassium nitrates, potassium ions, nitrate ions. Ionic solids, I cannot break apart. They stay as an ionic solid. And so if we take this reaction and then we substitute the ions where we can, lead nitrate again is lead ions and nitrate ions. If I have a bottle labeled 1 molar lead nitrate, I actually have a bottle with 1 molar lead ions and 2 molar nitrate ions. If I have a bottle labeled 1 molar potassium iodide, it's actually 1 molar potassium ions and 1 molar iodide ions, etc. And so we write down the ions for the potassium nitrate, the lead nitrate, potassium iodide, and the potassium nitrate. I cannot break apart the lead iodide solid because if I have lead iodide solid, I actually have lead iodide solid. And so we notice that we have potassium ions on either side. We have nitrate ions on either side. And so there are spectator ions. They're not involved in this reaction. If we write down the reaction without the spectator ions, we get the net ionic equation. And then looking at this, we should recognize that the net ionic equation is going to be 1 over KSP for lead iodide. And so again, the Ekman constant for the net ionic equation is also the Ekman constant for the reaction that we started with. And so sometimes when two solutions
in the
are
reaction
combined,
of the solutions of lead
is
nitrate
formed.
and potassium iodide, 2 compounds are produced. One is aqueous potassium nitrate, and the other is solid lead iodide, which precipitates from the solution as yellow particles.
And now the last type of Ekman constant we're talking about is the formation constant. And so when you have a metal ion with a ligand, like ammonia, forming a complex cobalt ammonia, the Ekman constant for that's going to be a Kf. Now again, if we reverse it, we're going to have to take the inverse. Now just like for Kas, there actually is Kf1, Kf2, Kf3. This is a little bit different than the Kas. For the Ka1 is removing the first hydrogen, for Ka2 is removing the second. For the formation constant, Kf1 is adding the first ligand. Kf2 is for adding the second ligand. Now we can look at a little bit harder problem. And so what is that Ekman constant for the following reaction? We have cobalt phosphate plus 6 ammonia going to the cobalt ammonium complex plus 2 phosphate ions. Now we have to come up with a series of reactions. When we add them up, we get this net reaction. And so notice that we have that cobalt phosphate solid. So we want to think about the KSP for the cobalt phosphate. And notice that we have the cobalt ammonium complex as a product. And so we might want to think about the formation of the cobalt ammonium complexes. And so if we add the 2 corresponding reactions, we get the reaction that we're looking for. Now the top reaction that we added was just the KSP of the cobalt phosphate. The second reaction that we added, the Ekman constant, is going to be the Kf1 times Kf2 to the power 3. Remember, if you multiply a reaction times the number 3, then you have to take the Ekman constant to that power. The reaction started as being a summation of the first Kf1 plus Kf2. And so if looking at the numbers, KSP is 2.05 times 10 minus 35th, and then Kf1, Kf2, and then we end with 6.3 times 10 minus 25th. And so we can ask ourselves according to the Le principle, should cobalt phosphate be more soluble in pure water or a solution that contains ammonia? Well, we know that if we add ammonia, we're adding a reactant, and so that should push the reaction towards the products. And it should be more soluble in a solution of ammonia, more will dissolve. We could also ask ourselves, based on the Ekman constants, should cobalt phosphate be more soluble in pure water or a solution that contains ammonia? In pure water, the Ekman constant is 2.05 times 10 minus 35th. In the solution with ammonia, you're looking at 6.3 times 10 minus 25th. And so that's 10 orders of magnitude more larger. And so it should be more soluble in a solution that contains ammonia. And so equilibrium constant is very helpful. That it can tell us if it's going to be product favored or reactant favored. Great stuff. Have fun with it.